All right, last video on partial fraction decomposition, which is the second of the two topics that we talk about in 5.7 of your book. In this video, I want to get into a couple special cases of partial fraction decomposition. There's exactly two of them, hence exactly two examples here. So if you're given these two problems and you recognize that you're supposed to do partial fraction decomposition, and you just started using the steps that we learned in the previous video, these 4 steps, maybe you just start by factoring the denominator. And in fact, that's exactly what you want to do. So for this first one, x squared plus 2x plus 1, maybe you recognize that that factors into x plus 1 times x plus 1. So I can rewrite the original expression as 3x squared plus 2x minus 1 divided by x plus 1 over x plus 1. And you're like, oh, okay, the factors are the exact same here. I wonder if that changes anything. Turns out that it does. When you have repeated factors in your factorization, you can't do things exactly the same as we did them here. You might think that you should make it a over x plus 1 plus b over x plus 1, right? That would kind of make the most sense logically because our two factors are x plus 1 and x plus 1. But it turns out that you can't do that. What you instead do, and there's no reason you'd know this unless I was telling you this, is you put a over x plus 1 just like you'd expect, but then for your next one, you put b over x plus 1 squared. Right? So because we have 2 copies of this, we need one of them to the first power and one of them to the second power. If, and this will never happen in this class, this were x plus 1 cubed was your factorization, if you had 3 of these, then you need x plus 1, a over x plus 1, b over x plus 1 squared, and c over x plus 1 cubed. And the obvious follow-up question is like, wait, why do I need that? And I don't have a great answer for you. It's just kind of, that's how the algebra works out. I mean, the whole idea with partial fraction decomposition is we want an algorithm that will allow us to write something that looks like this as something that looks like this. But if your denominator here is just x plus 1 times x plus 1, then we can't always write it as a number over x plus 1 plus another number over x plus 1. It just doesn't work out that way. And as we go through the algorithm, maybe you'll be able to see a little bit more about why that has to be the case. So at any rate, if we have these repeated factors, you just set it up this way. But that's it. Then everything else is the same. And what you'll see is things work out pretty nicely. What did I do next? Oh, right, I was trying to clear the denominators. So I'd multiply both sides of the equation by x plus 1 times x plus 1. On the left side, that would just leave me with the 3x squared plus 2x minus 1. And on the right side, now I got x plus 1 times x plus 1 up top. One of those x plus 1s can cancel with this x plus 1, but the other one sticks around, so I get a times x plus 1. And if I have x plus 1 times x plus 1 up on the top here, well then they both cancel out with these x plus 1s, and I'm left with just a b over here. This might look a little bit strange, namely we're not going to have any x squared terms on this side of the equation, but we will on this side of the equation. But don't worry about it, it's going to work out. My next step was to get rid of all the parentheses on the right. I'll do that same thing. I got ax plus a, and then plus b is equal to this same thing. Now we equate the coefficients. Note that you can't even do anything with the x squareds because I don't have any x squareds on this side of the equation, so I can jump right to my x's. And if I look at my x's, I have that 2 is equal to, well, the only coefficient I have with an a or with an x in it on the right hand side is this a right here. So based on my x's, I know that 2 must be equal to a. And then based on my constants, let's see, over here my constant is a -1, and over here my constant is a plus b. So I get these two equations, significantly nicer than they were in the last example. If a is equal to 2, well then I can plug that in down here, and I get -1 equals 2 plus b. If I subtract 2 from both sides of the equation, I get that b is equal to -3. I've solved for a and I've solved for b. I know what numbers go here and here, and that allows me to rewrite the original integral here as the integral of, instead of a over x plus 1, I can write 2 over x plus 1. And instead of b over x plus 1 squared, I can write -3 over x plus 1 squared. And now we need to integrate this, which is the only calculus part of this video, but it's actually the part I'm going to gloss over the most, because I think you can take all these antiderivatives, especially if I give you a couple little hints. For this first term, the 2 is a constant, so we can just pull it out in front. And then we just worry about the antiderivative of 1 over x plus 1, and that's the natural log of the absolute value of x plus 1. Remember, when your coefficient on the x here is just a 1, then we don't even have to worry about doing a u substitution. You can just write the natural log of the absolute value of x plus 1 here. And then for this next term, I have a -3 as my coefficient, so I'll pull that out in front. And then I'll ask myself, what's the antiderivative of 1 over x plus 1 squared? Well, the way to think about this is, if you were to do a u substitution, you don't have to write out all the steps unless it helps you. We can make u equal x plus 1. And if u were x plus 1, then du would just be dx. So I can just think about if this said du and this were 1 over u squared. Well, if it were 1 over u squared, that's just u to the negative second power. U to the negative second power, I could take care of that just using the power rule, right? Instead of writing u to the negative second power, I'd add 1 to the exponents. Now it'd be u to the negative first power, but I'd have to make this balance by dividing by 1 over that negative 1. Of course, I don't want to write a u here because I'll substitute the u back into x plus 1, and so this will end up being an x plus 1 here. Again, if you have a hard time following that, just do a u substitution. Maybe for the sake of notation, I'll write this off to the side, that both here and here, if you wanted to actually do the u subs, here's what you do. Try it on your own, and I bet you can get there. Don't forget to tack on your c, and then you're completely done. I'd probably rewrite this just because it's a little bit ugly. You've seen enough of these that you're probably expecting me to do as much. Let's see, negative 3 times 1 over negative 1. This is just negative 1. Negative 1 times negative 3 is positive 3. So I can put plus 3, but instead of 3 times x plus 1 to the negative 1 power, I can make that 3 over x plus 1, and then plus c. The point of all this wasn't supposed to be the calculus, although it never hurts to get practice with u subs. The point of all of this is just that when you have a repeated factor, you have to do partial fraction decomposition a little bit differently, namely including x plus 1 to the first power and x plus 1 to the second power. Next example is kind of similar in that it's a special case and that we'll have to do a little bit of calculus. But again, you'll see that the calculus here isn't all that involved. Most of the work is just dealing with partial fraction decomposition. So I'll start this out the same way I've been starting them out down here to the side by factoring the denominator. Notice these both have an x in them, so I can pull out an x and get x times x squared plus 1. There's a problem here. You may or may not recognize it. X squared plus 1 is problematic. It's what's called an irreducible quadratic factor. Maybe in like a pre-calculus class, you learn that all polynomials can be factored into either linear or quadratic terms. If you get lucky, they can be factored all the way down to linear terms, but sometimes you'll get these things called irreducible quadratic factors that can't go any further. X squared plus 1, if you picture the graph of that, it's a parabola shifted up 1 unit, and because it never crosses the x-axis, that means it doesn't have any real roots. And since it doesn't have any real roots, that means you can't factor it over the real numbers. So what that means is we can't go any further than this. We can't get linear factors down here. We can factor this, but one of the factors is irreducible quadratic. When you're in the case that one of the factors is irreducible quadratic, you can't just do this exact same a over b trick. What you'd probably think that you'd do in this case is you take each of your two factors, the x and the x squared plus 1, and write two different fractions with those as the two denominators, and so far that's exactly what you'd do. And over the first one, you'd be like, I bet I put an a here. Yup, you do. And over this one, you'd be like, I bet you put a b here. Nope, that's where things break down. When you have an irreducible quadratic factor, you can't just put a single constant up here. Kind of for the same reason we needed this x plus 1 squared here, because it doesn't work out. If you just have a constant right here, it's not necessarily true that we can rewrite this in this form. We want an algorithm that will always let us rewrite this in this form. In order to make things always work out in terms of all the algebra, we need to put a bx plus c here. So instead of just a constant, we need a linear factor here when we have an irreducible quadratic. What I'm saying is if you ever have x squareds in your denominator and you can't factor any further, it only works if these are irreducible. All you do is instead of writing a b up top, you write bx plus c. Just remember that, bx plus c, or whatever letters you haven't already used. And then when you get that far, everything else just rolls kind of the same as it's been. What we would typically do in our next step is we'd clear the denominators. Same logic here. Clearing the denominators on the left is really easy. I multiply both sides by x times x squared plus 1. This all cancels out and I'm left with just the top. But if I do that over on this side, I have an x and an x squared plus 1 up top here. The x's cancel, and so I'm left with a times x squared plus 1. In other words, ax squared plus a. Same idea over here. If I multiply x times x squared plus 1 times this factor, they'll all end up with an x squared plus 1 on the top and the bottom. So those cancel, and I'm left with just the x up top. The x times bx plus c gives me bx squared plus cx. And now I have this equation. It's kind of like I was at this step. I don't have any parentheses that I have to deal with. That's kind of nice. So all I have to do is equate my different coefficients. Let's start with the x squareds. If I look at my x squareds on the left-hand side, I got 2. If I look at my x squareds on the right-hand side, I got an a and a b. So 2 must be the same as a plus b. If I look at my x's on the left-hand side, there's no coefficient here, so there's the implied 1. So it's just one of the x's that I have on the left. On the right, this is the only term with an x in it, so 1 must be equal to c. And then I look at my constants. My constants on the left-hand side is the number 7. My constants on the right-hand side, it looks like it's just this a. So what I get from these three equations is that a must be 7, c must be 1, and I'll have to solve for b, but that's easy enough. If a is 7, I get 2 equals 7 plus b. It sounds like b must be equal to negative 5. Now that I have a, b, and c, I can just plug those in right here, and this will give me something I can take the integral of. See, if a is 7, I get 7 over x. And if b is negative 5 and c is 1, I get negative 5x plus 1 over x squared plus 1. I'm done with the partial fraction decomposition after I write this up here, but now it's time to start the calculus. It's kind of weird that these problems are 90% algebra. You do all this work down here, and then just the last little bit calculus. Most of the calculus has been easy, although you'll see in these irreducible quadratic factors, the calculus can be a little bit harder because of this bx plus c. Because we have a variable in the numerator here, it makes it a little bit harder to take the antiderivatives here. The 7 over x, that's still easy. That's just going to be 7 times the natural log of the absolute value of x. That's really easy. But for this one, I got a little bit of extra work to do. And the extra work that I'm going to do is I'm going to think about this as negative 5x divided by this thing plus 1 divided by this thing. I'm going to break up my numerator, because it's a sum of two terms, into the two different terms. Since I now have these two different terms, I can approach it as though it were two different integrals. First figure out this integral, then figure out this integral. I'm a little bit low on room, so maybe I'll figure out this integral down here. The idea with this one is you might notice that the numerator, the power here is just 1, and the denominator, the power is 2. When the power in the numerator is 1 less than the power in the denominator, a u substitution works out really nicely. I'm going to let u equal x squared plus 1, and then my du, the derivative of x squared plus 1, is 2x, so du equals 2x dx. In other words, half of du is equal to x dx. So I can pull the negative 5 out in front, and I can also take this 1/2 and put that out in front, so I get negative 5 halves out in front of my integral. And then changing the x squared plus 1 into u will leave me with 1 over u du. Make sure you can follow where all the different pieces go. I think that'll get you to this stage. And this stage is a great stage because we know the antiderivative of 1 over u. It's just the natural log of the absolute value of u. So my final answer will be negative 5/2 times the natural log of the absolute value of u. But rather than writing u, I'll write x squared plus 1. And then I'll tack on my plus c. So this answer right here, I can kind of transport this up into the problem that I was working on. I got 7 times the natural log of the absolute value of x is the answer for my first term. And then the antiderivative of the second term is this guy. And then for my third term, it might look bad, but it's actually great. Think about it for a minute. Do you recognize that as anything? Think inverse trig? This is exactly arctangent. So my final answer for this problem ends up being the sum of these three terms. And you might be like, whew, all right, we're finally done. You said 2 examples, that's 2 examples. This video should be over, right? Well, not really. It might have felt a little bit lucky that this was exactly arctangent, right? This 1 over x squared plus 1. The 1 part wasn't lucky, because if this were like a 3 or something, I could take that and factor it in front of the integral. But having x squared plus 1 here was kind of lucky, right? There's other irreducible quadratic factors, x squared plus 2, for example. What if instead of being 1 over x squared plus 1, this was 1 over x squared plus 2? Well, if this were 1 over x squared plus 2, then it doesn't work out to just be arctangent. You're like, well, if it's not arctangent, then what is it? What we need to do is make this a 1. It's currently a 2. I wish it were a 1 so it would look like arctangent. The way I can do that is I can factor out a 2. But you're like, wait, you could just take a 2 from here but not everything else? No, the idea is I'm going to factor out a 2 from everything in the denominator. If I factor out a 2 from everything in the denominator, it changes this 2 into this 1. And you're like, oh, great, that solved that problem. Well, not really, because while it fixes this 2, it messes up this x squared. Now I have 1/2 x squared here. If I want the antiderivative of this thing to be arctangent, this has to be x squared plus 1, not 1/2 x squared plus 1. So it might seem like by fixing something, I screwed something else up. But there's a way to fix this without messing this up, and it's to do a u substitution. And this falls into the category of stuff that you shouldn't see on your own, but maybe after I show you, you can kind of follow it. If I took this 1/2 and brought it out in front of the integral, just so I didn't have to mess with it, I could rewrite the denominator here, 1/2 times x squared, as 1 divided by the square root of 2 times x, all squared. And I know you don't see why to do that right now, but can you at least follow that if this whole thing were squared, I'd square the x to get x squared, and I'd square the 1 over the square root of 2, but 1 squared is 1, and the square root of 2 squared is 2, so this is the same as 1/2 x squared. The advantage to writing it this way is now you can do a u substitution to fit this into the arctangent form. If I take this stuff inside the parentheses and I call that u, so I'll end up with 1 over u squared plus 1, I'll end up in my arctangent form. Well then, u is 1 over root 2x, then du is 1 over the square root of 2. Because when you take the derivative of a constant times x, the x goes away and you're left with just the constant. But I don't have a 1 over root 2 dx. I can multiply the root 2 over to the other side and get the square root of 2 times du is equal to dx. And now I can go doing all of my substitutions. I still have the 1/2 out in front, and then when I change my dx into the square root of 2 times du, I can take that square root of 2, since it's just a constant, and put that out in front of the integral, and then I will have 1 over, instead of 1 over root 2x, that's exactly what u is equal to, so I got u squared plus 1 du. And this finally fits that arctangent form. So you can kind of see how we were lucky down here that we had a 1 in this spot. Because if you didn't have a 1 in this spot and you had any other number in that spot, well, first you would factor it out in front, but that would screw up your x term, so you'd have to do a u substitution to fix your x term to get back in that arctangent form. What I'm saying is this integral that we started out with here would be equal to the square root of 2 over 2, if I put these two constants together, times the arctangent of u. And it's worth pointing out that I don't want to leave u in my answer because u is 1 over the square root of 2x. Did you follow all that? Because that's really hard. Your book doesn't think you can follow that. I think you can follow it, so I showed it to you. I wouldn't test you on this, but I think you can follow it, so I showed you this. Let me show you what your book does. Your book totally cops out. What it does is it's like, hey, by the way, if you ever ended up with 1 over x squared plus some other number, so like we had x squared plus 2, so playing the role of a here is the square root of 2, they're like, hey, here's just a formula. There's a formula you can always use, and you can verify it's true by taking the derivative of the right and seeing that gets you back to the left. They're like, no way the student could ever figure out how to do the algebra that we just did in that video. So let's just provide that as a separate formula. And that way, if they ever get to something like x squared plus 4, they can just directly apply this formula and say whatever your value of a is. Remember, in our case, the value of a was the square root of 2. Our answer would be 1 over the square root of 2, arctangent of x divided by the square root of 2, which you'll see is exactly what we got over here. Let me preemptively answer the follow-up question. Am I going to be tested on this? No. In a word, no. You would never have to do this on a test. If you can do this, I don't know, maybe you could earn some extra credit for it somewhere, but I would never expect you to be able to remember all these steps. Because realistically, if I was testing partial fraction decomposition and I put this in here, so many students would have a hard time just with the factoring or just with correctly getting the A and the B's, or there's so many different steps that you can mess up along the way, that when I test partial fraction decomposition, I try to keep it the easier cases. And so as far as doing this u substitution, you would never have to worry about this in the context of a partial fraction decomposition problem. I think it's cool if you can do it, but I wouldn't worry too much if you can't.